So continuing on from our previous video, we know about the point of tangency, the point at which f is maximized along the function g of xy equals c, is when the gradient vectors are proportional to one another. So we found the two gradient vectors, and they'll be proportional for some value of lambda under this equality. And so I can write the two components separately, because that means that if this guy is being scaled by lambda, that scales both components. So the gradient in the x direction, or the slope in the partial in the x direction is proportional to the partial in the x direction here. So we get this first equation, and the partial with respect to y is proportional to the partial with respect to g, and so we get these two equations here. So what our objective, because we don't really care about lambda, we're just using this sort of as a pivot, as a mathematical pivot more than anything. And it's just a quick little trick that what we want to do is we want to take these two equations and try to combine them in a way to eliminate lambda from the picture. The easiest way to do this oftentimes is to just divide one equation by the other, because division is a great way to eliminate things, especially if there's something common. So I'll divide the left side by the left side and the right side by the right side, and you'll see we do this in the next example as well. So dividing the two equations eliminates lambda, so we get this side divided by this side equals this side divided by this side. And so we do a little bit of reduction here, properties of exponents. We get reduction of a factor of 2, x to the negative first, negative 0.4 minus 0.6, and then y to the 0.3 divided by y to the negative 0.7, which is y to the positive first, and that equals lambdas cancel, 40 divided by 10 is 4. And so all I'm using this for, this is just an equation that I want to use to help me now mathematically determine what value of x and y represents a critical point. So all I've done is I've just exploited the structure of all things to come. And so next we're going to use this equation that we've derived, and this is typically what we do each and every time, is now we take our constraint and we simultaneously solve these two equations for x and y, because now I obtained the second equation from using this concept of knowing that the gradients are proportional to one another. So we're going to use g of xy equals c along with the above constraint to find the critical point, and we're going to do this in Desmos because it's often not trivial to solve these equations, though it can be done. This one's not too terribly bad. You can use substitution and all that. But we're going to plot our constraint that came out of the Lagrange equation, and we're going to plot our actual constraint, and we'll do that over in Desmos. So let's take a look. Here's 2x to the negative first times y equals 4. Here's 40,000x plus 10,000 y equals 600,000. Just to prove to you that it doesn't change anything, I can divide both sides by 1,000 and I'll still get the same intersection point. And so now the intersection point is the point 10, 20. Well, guess what? That is the critical point on the original function that satisfies, well, clearly it's on the constraint line. We can see that. And using this idea of Lagrange, I was able to develop this first constraint here that allows me to intersect these two equations. And now I'm claiming that 10 doctors and 20 nurses, well, hey, that's what we saw over here as well. Whenever we changed, should be 600. Whenever we found that point of tangency, we found it to be about 9,780, which, to be exact, comes out to, well, let's see, our total number of visits will equal 1,000 x to the, let's see, x to the 0.6, y to the 0.3. Just grab that there. And for x, I'll plug in 10. And for y, I'll plug in 20. All I'm doing checking here is that the number of visits ends up being should be 1,000, the 9,780. So I come out to more precisely 9,779 visits to maximize the number of visits and be able to stay at budget. So that really solves our problem. We're pretty much done. But the last step is just, of course, to ensure that that critical point is a maximum. So we've just shown that having 10 doctors and 20 nurses gives us this many visits, but we want to ensure that that's a maximum. So I'll let you do this, but you should always use the second derivative test or some form of verification to ensure that we haven't accidentally minimized the total number of visits, because this is just a critical point. That's all it is. Critical points could be local mins or local maxes. Sometimes none of the above, I suppose. So that's kind of how we use this idea. Well, let's do this for another problem. Let's say that we want to design a box, and we want to maximize the volume of this box. It's going to be 2 inches tall. I originally had 2 feet, and then all my units were off. So let's just pretend 2 inches is a good height. So maybe it'll carry a book of some sort. And it's 2 inches tall, and we have a constraint on it now. We want to make sure we use 1,000 cubic inches of cardboard. We don't want to use any more than that. This is our limit. This is how big our sheet of cardboard is, and we want to use it all up. We don't want to have any waste left over. So first of all, we have to ask ourselves the important questions, which are, of course, what are we trying to do? Well, there's our box. So we want to design the box, so that leaves us with a length and a width that we could determine, but we want it to be 2 inches tall. So x and y are the length and the width, and we don't know those yet. So I'll kind of step through this carefully. So we want to maximize the volume, and the volume is length times width times height. So there's the height, there's the length, there's the width. When you multiply those together, you get volume. Now we want to subject it to the fact that we have 1,000 square inches of cardboard to use. Well, where are we going to use that cardboard? Well, we're just going to assume for simplicity that we have 2 sides. We have this side and we have this side over here, and each of those 2 sides as 2 inches tall by x inches long. So each of those will be 2x square inches. And then the 2 sides, or the 2 ends here and here, and those are each y inches wide by 2 inches tall, so 2 times y. And because I have 2 of those, I'm going to have 2 of those terms in there. And then I'm going to assume that I've got the bottom, which, of course, is hidden back here. So I've got the bottom hiding back here. And the bottom is going to be x inches long by y inches wide. And I'm also going to make the oversimplifying assumption that I know see these flaps on the top, but I'm going to make the oversimplifying assumption that that basically I can just kind of take a scrap of cardboard and tape it to the top, and then I'm not going to have these flaps to deal with. So we'll just keep that real simple. So now I have 2 of every term, so I have 2 yx's. That comes from these 2 guys here. And then I have 4 y's, because I have 2y and then 2 more y's. And then I have 4x, because I have 2x and then I have 2 more x's. And what I want to ensure, that's my total surface area. So this is really a surface area constraint. And I want my total surface area to end up being 1,000 square inches of material. So now I can begin doing the calculus on this. So we know that now that we know that well, first of all, I suppose I could explore this once again in a graph. And so now I have 2xy equals v plotted, and I have my surface area function. You can see my volume function is the red one, and my green function is the constraint one that isn't changing. And so now I'm just going to find where I maximize volume, and it appears to be pretty close around, I don't know, 20 point something, 20 point something, and I'll be able to get a volume of about 840 cubic inches out of that box. So if that for ideas here is the same, then we should be able to find the 2 gradient vectors. So the gradient for v is 2y and 2x, the 2 partial derivatives. The gradient for g, now remember g is just the right side of this, so that's g of x and y, and g of x and y equals 1,000 is my constraint. So I'm just taking the partial derivative of that portion there, and so that gives me 2y plus 4, 2x plus 4, and now I'll step through. Okay, I've got to identify that this gradient vector is going to be proportional to this gradient vector, where those 2 are tangential to each other. So that means I'm going to set 2y equal to lambda times 2y plus 4, and 2x equal to lambda 2x plus 4. And once again, just like in the previous example, to eliminate the lambda, that's my objective. I don't really care what its value is. It's just a scalar multiplier. I'm going to divide the 2 sides by each other. So 2y divided by 2x, the 2's cancel. I'm left with y over x. Divide lambda times 2y plus 4, lambda times 2x plus 4. The lambdas cancel, and I'm left with 2y plus 4 over 2x plus 4. Well, you guessed it. Now what we're going to do is we're going to take our constraint equation, and our Lagrange equation, we're going to plot those and we're going to find out where those two suckers intersect. So I'm going to come over here, over to Desmos. So I have that Lagrange equation plotted. I have my constraint equation plotted, and the point that optimizes the volume of the box is 20.45 comma 20.45, and the actual volume will be 2 times 20.45 times 20.45, and we see that that's about 836.4 cubic inches, which guess what? That's not far off from what we actually came up with. We're off by about 4 units, but only because it's just hard to eyeball off the look of things from looking at the graph. So our final interpretation, again, we should verify that this is a maximum and not in fact a minimum, so with using the second derivative test. But if we make the base of square dimensions, 20.5 by 20.5, we get a maximal volume of, this should read 840.5, that's because I rounded to 20.5, of 840.5, this should be cubic feet, and that shouldn't be there. So that's how Lagrange optimization works. It's a fairly straightforward process once you get the idea down. The functions can change. The hardest part is, of course, modeling and writing the objective equation and writing the constraint equation. But mathematics works out fairly nicely most of the time, unless, of course, you're going to try to solve some of these systems of equations by hand. More power to you, but we're not going to do that here. So that's it for the video. Hopefully it's been helpful, and we'll talk to you soon.